My name is Estanislao Claucich. I'm presenting our paper called Fairness of Deep Ensembles on the interplay between per group task difficulty and underrepresentation. So when training a model, it's common to have that for some reason, the model is going to underperform for some group and overperform from another one, for any reason. And that will lead to a high subgroup accuracy gap between these two subgroups and basically end up with a biased model. So there are going to exist a lot of techniques to address these biases. On this work, we focus on how model ensembling can be used to address these kind of biases, because it was already proven that model ensembling can help to improve the performance of both subgroups at the same time, so basically reducing the subgroup accuracy gap between them. So we focus on this technique. But this raises the question of why or even where this discrepancy on performance even come from. So a common scenario is to have that when training the model, you can have like an unbalanced scenario between the two subgroups. So we can have a subgroup that is going to be underrepresented during training, and that will lead again to a model that is going to be biased towards this subgroup that is underrepresented. Once again, to a high subgroup accuracy gap and a biased model. So basic techniques to try to solve this or address these kind of biases is to use some balancing techniques. So the idea will be just to have the same representation of both subgroups during training to try to achieve a better accuracy gap between them, to lower this accuracy gap. But this discrepancy in performance can also be explained, for example, with a per group task difficulty discrepancy between the two subgroups. There can be cases where one subgroup can be, for some reason, more difficult. The task could be more difficult for one group than for the other one. And that, once again, will lead to a model that is going to underperform on that group that was most difficult than for the other one. Once again, to a subgroup accuracy gap and a biased model towards this group that is more difficult. So on this paper, we focus on these kind of scenarios where we have this per group task difficulty discrepancy. And we ask ourselves if we can use these techniques of model ensembling and rebalancing techniques in these kind of scenarios to try to address the biases and achieve a lower subgroup accuracy gap using these techniques on these particular scenarios. So just to get a little ahead of myself, on this paper we proved that by using an imbalanced scenario where you have overrepresentation of the most difficult group, is going to be better than using a balanced scenario where you have the same representation for both groups. That imbalanced scenario is going to help to improve the performance of both subgroups at the same time and reducing the accuracy gap. So I'm going to show you only the main experiments and results that led to this conclusion. And if you want to check the full paper, you can scan the code, or we can talk about it later. So we started with a fully completed synthetic scenario where you have some binary classification problem that is going to also be explained by some binary property attribute. Just for simplification, let's call it, we have male and female. I'm going to play around this scenario with two variables. On the first hand, we have a balance ratio, so the representation of male and female during training. So I can go from a completely balanced scenario where we have the same representation of male and female, and I can go to a overrepresentation of female during training or a overrepresentation of male and every value between them. And on the other hand, I'm going to play around with this variable that is going to be some additional female difficulty that I'm going to add. So for the subgroup of female, I'm going to add some difficulty so I can make it more and more difficult, that subgroup, than the other one. Yeah? So playing around with these two variables, I can have like any combination for them. I'm showing you here just an example of having a fixed balance ratio of an overrepresentation of female and this additional added difficulty for that same group. Yes, let's think about like some... It can be anything, but let's think that the group is becoming more difficult because I'm adding some noise or something like that. But it's becoming more the task is becoming more difficult for that group than for the other one, because I'm adding some constraint or something to that group that I'm not adding to the other one. So we can talk it about later, but let's say that I train a model under this scenario that I talked about. So I'm showing you here the performance of the model for female and male under this additional female difficulty that I'm adding. So if you see a starting point, you're going to see that if I don't add any difficulties, so the same initial starting point for difficulty for both groups, the group that is going to overperform is going to be the one that is overrepresented during training, in this case, the female one. But as I'm starting to increase the difficulty for that same group, its performance is going to start to decrease. until you reach a point where the performance for both male and female, the overrepresented group and the underrepresented group, is going to be the same. Because the overrepresented group is much more difficult than the other one. So it's going to reach a point where the performance is going to be equalized. So we wanted to take a closer look to that particular scenarios and to use these ensembles techniques to try to address the biases. So what I'm showing you here is exactly that, the same point that I showed you before, an overrepresentation of female, and with this high added difficulty for that same group. And I'm showing you the performance of both male and female, but under an increasingly sized ensemble. So we go from an ensemble of only one model, one single model, up to an ensemble of 20 models, and you can see how the performance is going to vary across that increasingly sized ensemble. And at the same time, I'm showing you what is going on this imbalance scenario of having an overrepresentation of female in the solid lines. And on the dashed line, I'm showing you what would happen if we have decided to balance this scenario. So under this additional difficulty, what would happen if we decided to use the same representation of both male and female and not an imbalance ratio as I'm showing you in the solid lines. So the first thing that you can see is that on the imbalance scenario, we achieve a better overall performance than on the balance scenario. And not only that, we achieve a lower gap between the two subgroups of males and female on this imbalance scenario than on the balanced one. This is what we are going to call a positive sum fairness, because we are achieving a better accuracy gap between the two subgroups by improving at the same time the overall performance of the model on this imbalanced scenario than on the balanced one. So once we got these results on the synthetic scenarios, we went and tried to replicate them on real scenarios. So we used two images dataset, Celeve and Shakespeare. On both of them, we have some binary classification problem. On the case of Celeve, we have the problem of classifying between bland and not bland people. And on Shakespeare, we have the problem of opacity, whether if it's positive or negative. And in both cases, we have this information of binary prothetic attribute of male and female, so we can do the same analysis as we did before with the synthetic scenarios. So what I'm showing you here is, for Celeve, the same results that I showed you before in the synthetic scenarios, how by an increasingly sized ensembles, the performance is going to vary. So you can see that, once again, on the first thing that we did was to try to identify which one of these two subgroups, male and female, was the most difficult one in this case. So in this scenario, the male one was the most difficult one, because on a balanced scenario, it was the one that underperformed. So that was the one that was identified as the most difficult one. And based on what I showed you before, that would mean that we are going to need more samples of that group, because it's the most difficult one, to try to achieve this positive sum scenario. And that's what I'm showing you here. I have an overrepresentation of male that was the most difficult group, and we can achieve a better overall performance of the model on this imbalanced scenario than on the balanced one. And not only that, but also at the same time reduce the gap between the two subgroups on this imbalance ratio. Once again, achieving positive sum fairness on an imbalanced scenario than on the balanced one. And on Shakespeare, we saw the same thing, the same similar tendencies, only that in this case, the discrepancy of difficulty between males and females was not that high. So the shift that we needed to do to achieve positive sum fairness from that balanced scenario was also not that high. But once again, we could achieve some positive sum fairness scenario on an imbalanced scenario than on the balanced one. So just to sum up on this work, what we did was to work on these scenarios where we have a discrepancy, a per group that's difficulty discrepancy, where one group is going to be more difficult than the other one. And we proved how using model ensembling techniques and balancing techniques, basically using an imbalance ratio between the two subgroups, you can achieve positive sum fairness by overrepresenting the group that was identified as the most difficult one. So that's going to lead to a better scenario than using the same representation for both subgroups during training. So thank you all.